So today we have discussed here governing of hydraulic turbine. The governing of turbine is defined as the operation by which the speed of turbine is kept constant under all working conditions. Means actually in turbine power plant means water turbine power plant or impulse water turbine power plant, reaction water turbine power plant. Our turbine speed is very continuously because of fluctuating load. So see, so it is necessary to control the speed of the turbine at a constant speed. That's why we are required to control the speed of turbine shaft. So how to control this speed? So that's why we are required governing procedures. two, two to three governing procedure to control the speed of turbine. So see here, what is governing? Governing of turbine is defined as the operation by which the speed of the turbine is kept constant under all working conditions. So governing of turbine is necessary as the turbine is directly coupled to an electric generator which is required to run at constant speed under all fluctuating loads conditions. It is done automatically by means of governor which regulate the rate of flow through the turbine according to the changing load condition on the turbine. The governor used in hydraulic turbine should be very strong as it has to deal with the water coming at very large force and huge quantity. Here we have used governor for controlling the speed of the turbine. So actual function, control speed of turbine with fluctuating load at synchronous speed of generator. So synchronous speed is the constant speed of the generator. So high governing of hydraulic turbine is required as a turbine is directly coupled to the electric generator, which is required to run constant speed. The load of the turbine is constant throughout the day or hour in speed of turbine vary with respect to load at constant head and discharge. Therefore, in order to have constant speed of generator, governing of turbine is required to maintain the constant speed of turbine with respect to load. So main part of governing of Pelton wheel. First one, centrifugal governor used. Second, oil pump, gear pump with oil sump. Third, relay or control valve. Fourth, servo motor with spear rod assembly. Fifth, deflector mechanism. So, governor and linkage, a centrifugal governor is used as the measuring element of the closed loop control system. It is driven by turbine shaft through bevel gears. The sleeve of the governor is connected through linkage to relay valve. The movement of is transferred through the lever to move the piston rod of relay valve. Oil pump and oil sump system use oil in servo motor or relay cylinder since the force required to actuate the spear valve would be enormous. So for this reason, the system requires an oil sump to store the oil and oil pump to regulate the oil supply in the mechanism. So oil pump is positive displacement type of pump like gear pump or axial piston pump. Its function is to pressurize the oil. So relay and control valve functions. So relay valve is spool valve having 5 ports. It is also called as control valve or distributor valve. It receives the pressurized oil from the oil pump, which is diverted toward the ports to pipe A or pipe B. Through this pipe, the oil is transferred to corresponding site of double acting servomotor cylinder simultaneously, the oil will be returned from servomotor from the opposite pipe of the sump. So see here, system use oil in servomotor or relay cylinder, since the force required to actuate the sphere valve would be enormous. For this reason, the system required an oil sump to store the oil and oil pump to regulate the oil supply in the mechanism. Oil pump is positive displacement type of pump like gear pump or axial piston pump. Its function is to pressurize the oil. Servo motor or relay cylinder, it is double acting cylinder which act as a hydraulic actuator. It receives oil from relay valve, say through pipe A. The piston of the cylinder will be displaced toward left, thus the forcing the oil through the pipe B into the relay valve and finally to oil sump. It will simultaneously move the sphere valve to the left and increase the area of the flow through the nozzle. Here we have seen centrifugal governor diagram of governing mechanism of controlling the speed of turbine. This is centrifugal governor. You can see here. 1 minute. So you can see here centrifugal governor, fly ball. This is fly ball. Sleeves to turbine main shaft, lever, fulcrum, piston rod of the control valve, relay or control valve. See here, this is V1 position, V2 position. This is relay cylinder or servo motor, piston rod of the relay cylinder, and this is sphere nozzle assembly to control the flow. So this is oil pump here, oil sump. So this is photograph, actual photograph of centrifugal governor. So see here, in that case, here speed is increased. This governor or pry bar go upward direction. See here, in this diagram, you can see clearly. To increase speed, this governor pry bar move upward direction like that. In that case, to increase speed, see here, to increase speed, this position. After that, this fulcrum goes down to increasing the speed like that. So valve V1 is closed and V2 is open. So oil coming from V2 means here controlling in servo motor, this piston move forward direction and close the flow control valve by nozzle sphere assembly like that. So see here distribution valve to increase speed, rated speed lever we have seen here like that, controlling the speed of the turbine. So here working when the load of I have told this is given in theory part. When the load of the generator decrease, the speed of the generator increase. In speed of the turbine also increase beyond the normal speed. The centrifugal governor, which is connected to the turbine main shaft, will be rotating at an increased speed, and hence centrifugal force on the pry ball increases and it move upward. Sleeve of the governor will also move upward. As the sleeve move upward, a horizontal lever turns about the fulcrum and the piston rod of the control valve move downward. This closes the valve V1 and opens the valve V2 as shown in figure. The oil pump from the oil pump to the control valve under pressure will flow through the valve V2 to the servo motor and will exert force on the face A of the piston of relay cylinder. So piston along the piston rod and sphere will move toward the right. This will decrease the area of flow of water, means reduce the flow of the water at outlet of the nozzle, and it will reduce the rate of flow of water. Turbine which consequently reduce the speed of the turbine. So meanwhile, bell crank lever move downward, the jet deflected will operate and divert whole of a part of jet away from the bucket. As soon as speed becomes normal, the pry balls and sleeve lever and piston rod come to the its normal position. Multi-jet pattern wheel, higher rotational speed, smaller runner, simple flow control possible, redundancy, can cope with large range of flow, but need complex method, may take control governing complex. Number of jet may be increased usually up to 4, but never more than 6 because higher number of jet makes the governing complicated. We can see here, this is number of jet 1, 2. This is bucket. This is called double jet Pelton wheel turbine. Now cavitation, the liquid enter the hydraulic turbine at high pressure. This pressure is combination of static and dynamic component. Thus the cavitation can occur near the fast moving blade of the turbine where local dynamic head increase due to action of blade which causes static pressure to fall. So cavitation of Thoma number. Sigma is the Thoma number. So Pa is the atmospheric pressure, PV is the vapor pressure, HS is the elevation about airways, H is the total head, R is the density, and G is the gravity, like that. So difference between impulse turbine and impulse water turbine and reaction water turbine. So in hydroelectric power plant, mainly impulse or reaction turbine are used to generate electric power. From the engineering point of view, both have some differences in working of parts. Here, in this article, I am trying to share the knowledge with you. So, main difference of impulse and reaction turbine. First, in impulse turbine, the water flow through the nozzle and impact on the buckets, whereas in reaction turbine, water is guided by the blade to flow over moving vane. So, second, the impulse turbine, the entire water energy is first converted into kinetic energy, but there is no energy conversion in reaction turbine. In impulse turbine, the water impact on the bucket with kinetic energy, whereas reaction turbine, the water glides over the moving vane with pressure energy. Means simply in impulse turbine, our pressure energy convert into kinetic energy, and in reaction turbine, both energy are present. In this impulse water turbine, bucket with kinetic energy, where reaction turbine water glide over the moving vanes. In impulse turbine, buckets are peaks, and reaction turbine buckets are varies, means direction is varied. In impulse turbine, the work is done only by changing kinetic energy of the jet, but in reaction turbine, the work is done partly by the change in velocity head, but almost entirely by the change in pressure head. In impulse turbine, the pressure of flowing water remains unchanged and is equal to atmospheric pressure, but in reaction turbine, the pressure of flowing water is reduced after gliding over the vanes. In impulse turbine, it is not essential that the wheel should run far. Moreover, there should be free access of air between the vanes and wheel, whereas it is essential that the wheel should always run full and kept full of water in reaction turbine. In impulse turbine, the water may be admitted over part of the circumference or over the whole circumference of the wheel. But in reaction turbine, the water must be admitted over the whole circumference of the wheel. It is possible to regulate the flow of water without loss in impulse turbine, but in reaction turbine, it is not possible to regulate the flow without loss. This is difference between impulse turbine and reaction turbine. Now, application of Pelton wheel. So, Pelton wheel are preferred turbine for hydropower when the available water store has relatively high hydraulic head at low flow rates. Means we are required high head for Pelton wheel. So, Pelton wheel are made in all sizes. There exist multi-ton Pelton wheels mounted on vertical oil pad bearing in hydroelectric plant. The largest unit can be up to 200 megawatt. The smallest Pelton wheels are only a few inches across and can be used to tap power from mountain stream having flow over a few gallons per minute. Depending on water flow and design, Pelton wheel operate best with head from 15 meter to 1800 meters, although there is no theoretical limit. Pelton wheel is most efficient, thus more power can be extracted from the water source with high pressure and low flow than from a source with low pressure and high flow. The small units are recommended for use with 30 meter or more of head in order to generate significant power level. Now, selection of Pelton wheel turbine. Hydraulic turbine use water pressure to rotate its blade and generate energy. Selecting appropriate type of turbine depend on primary on available head and less so on available flow rate. The three primary types of turbine: Pelton turbine for high head, Francis for medium head, and Kaplan for low head. So for wide range of heads, several other types of turbine exist on market described below. To understand the operating characteristic of reaction and impulse water turbine, encompassed in their governing mechanical laws that predicts their work and performance. Demonstrate the mechanism of the turbine speed control in the relationship with various forms of energy explained in mechanical laws that predict their behavior. So selection of type of turbine, the selection of the best suitable for any particular hydro site depend on site characteristic. The dominant one being the head and flow available The selection also depends on the desired running speed of the generator and other device loading the turbine. Other considerations such as whether the turbine is expected to produce power under part flow condition also play important role in the selection. All turbines have power speed characteristics. They will tend to run most efficiently at the particular speed, head and flow combination. In large-scale hydro installation, Pelton turbines are normally only considered for head above 150 meter, but for micro hydro application, Pelton turbine can be used effectively at head down to about 20 meter. Pelton turbines are not used at lower head because their rotational speed become very slow and the runner required is very large and heavy. So if runner size and row speed do not pose a problem for a particular installation, then Pelton turbine can be used efficiently with fairly low head if higher running speed and smaller runners are required. Then there are two further options. Increase the number of jet. Having two or more jet enable a small runner to be used for given flow and increase the rotational speed. The required power can still be attained. The part flow efficiently is especially good because the wheel can be run on reduced number of jet, which each jet in use still receiving the optimum flow. Twin runners, two runners can be placed on the same shaft, either side by side or opposite side of the generator. This configuration is unusual and would only be used if number of jets per runner had already been maximized, but it allows the use of smaller diameter and hence faster rotating runner. Now, after discussing the selection of turbine, we have discussed characteristic curve of a turbine. These are curves which are characteristic of particular turbine which help in studying the performance of turbine under various conditions. This curve pertaining to any turbine are supplied by its manufacturers based on actual test. The data that must be obtained in testing a turbine are following: speed of turbine, discharge, net head, power developed, overall efficiency, and gate opening. This refers to percentage of the inlet passage provided for water to enter the turbine. Means actual gate opening is in the form of percentage, number of percentage. The characteristic curve obtained are following: constant head curve versus main characteristic curve, constant speed curve versus operating characteristic curve, constant efficiency curve versus curve. So what is constant head curve? Here, maintaining constant head, the speed of turbine is varied by admitting different rates of flow by adjusting the percentage of gate opening. Means maintaining constant head means take a constant head and the speed of the turbine is varied by admitting different rate of flow by adjusting percentage of gate opening. The power P developed is measured mechanically, and from each test and unit power, the unit speed and unit discharge overall efficiency are determined. The characteristics curve drawn: unit discharge versus unit speed, unit power versus unit speed, and overall efficiency versus unit speed. So constant speed curve in this case, tests are conducted at constant speed varying the head h, means suitably adjusting the charge. The power developed P is measured mechanically. The overall efficiency is aimed to maximum value. The curve drawn are power versus discharge, head versus discharge, head versus power unit power, maximum head versus percentage of full load. Means here we are test conducted at constant speed varying the head, suitable adjusting the discharge. Now constant efficiency curve. Here these curves are plotted from data which can be obtained from the constant head and constant speed curve. The obtained object of obtaining this curve is to determine the zone of consultant efficiency so that we can always run the turbine with maximum efficiency. This curve also gives a good idea about performance of turbine with various efficiency. Means these curve are plotted from the constant efficiency curve are plotted from the data which can be obtained from constant head and constant speed curve. The object of obtaining the curve is to determine the zone of constant efficiency so that we can always run the turbine with maximum efficiency. We can see here characteristic curve, efficiency and jet speed ratio. Here efficiency versus speed at various nozzle setting, like that. Power versus speed, we can see this is various nozzle setting. Now this is variation of efficiency with load at constant head. This is various characteristic load, discharge versus unit speed, unit discharge versus unit speed, unit power versus unit speed, unit efficiency versus unit speed. Main characteristic curve. This is power versus discharge. This is unit head versus power and unit head versus full load. Operating characteristic. Main characteristic. Discharge unaffected by speed of rotor, jet come out at pre-jet from the casing of the turbine. Power increase first to maximum with the increase the speed and decrease with the increase in speed. This is due to the fact that as the speed of the rotor increase, the jet does not have enough time to make impact of buckets. Operating characteristic, maximum efficiency 20% to 30% of load and constant afterward. Discharge increase parabolically, output varies linearly, power is zero for essential discharge as it is lost in overcoming the friction and inertia effect of the rotating parts. ISO efficiency means efficiency constant graph. Now, next, specific speed. See here, it is the speed of turbine which is identical in shape, geometrical dimension, blade angles, and gate. Opening with actual turbine, but of such a size that is will develop unit power when working under unit head. It is used in comparing the different type of turbine, as every type of turbine has different specific speed. It play important role for selecting the type of turbine, predicting the performance of turbine. So consider P as the power developed by the turbine. Means actually geometrical similar model we have taken produce unit power under unit head. So where n specific speed of the turbine, h is the head and n is the speed of the turbine, p is the power developed by turbine. So ns specific speed equal to n under root of p h raised to 5 by 4 to predict the performance of turbine and to compare different types of turbine. Derivation of the specific speed. So overall efficiency equal to shaft power upon water power. So power developed upon shaft power means power developed upon water power rho g QH upon 1000. So power equal to overall efficiency power developed into rho g QH upon 1000 is directly proportional to Q and H. So now D is the diameter, actual diameter of turbine. N speed of actual turbine, U tangential velocity of turbine, and N S is the specific speed of the turbine, V is the absolute velocity of turbine. So U directly proportional to V and V directly proportional to under root of 1/2. So H, V directly proportional to under root of H. So U directly proportional to dn under root of h directly proportional to dn, d equal to under root of h upon n. So after that, we know discharge directly proportional to d square into under root of h. So d square directly proportional to h upon n square into under root of h. So h equal raised to 3 by 2 upon n square. So power equal to h raised to 5 by 2 upon n square. So P equal to K h raised to 5 by 2 upon n square. K is the constant of proportionality. For now we are putting power, unit power and unit head in this formula. So we are getting constant K equal to ns square. So put this value, constant value in our above equation. After putting, we are getting P equal to ns square into h raised to 5 by 2 upon n square. So after rearranging our mathematical step, we are getting ns specific speed equal to n under root of p upon h raised to 5 by 4. This is our specific speed equations. In our equation, if P is taken in metric horsepower, the specific speed is obtained in MKS unit. But if P is taken kilowatt, the specific speed is obtained in SI unit. So after that, unit quantities. The result of turbine when expressed in terms of unit head, unit discharge, and unit power output are called as a result on unit quantities. The condition of turbine under unit head are such that efficiency of turbine remain unaffected. So unit head is defined as the speed of turbine working under a unit head denoted by Nu. So here simple derivation for unit speed. U directly proportional to V, V directly proportional to under root of H. So U directly proportional to under root of H. We know U tangential velocity calculated by pi dn by 60. So D is the diameter of wheel. So from above equation, U directly proportional to N. So N directly proportional to U. So N directly proportional to under root of H. N equal to K1 under root of pH. K1 is the proportionality constant. So now for unit conditions, we have put H equal to N1 and N equal to Nu. After putting this value, we are getting Nu equal to K1 So n equal to nu under root of ph means unit speed equal to n upon under root of ph. Now unit discharge defined as a discharge passing through a turbine working under unit head, so denoted by QU. So Q is the discharge passing through the turbine when head H is on the turbine. A is the area of flow of water. Head under which turbine is working, that is called H. So Q is the area of flow in x velocity. So, but the area of flow is constant. So velocity directly proportional to under root of ph. So Q equal to K2 under root of ph. K2 is the constant of proportionality. So put unit value h equal to 1, then Q equal to QU for unit discharge. Now unit discharge equal to K2. So put this value in our equation. After putting, we are getting Q equal to QU under root of H, means unit discharge equal to Q upon under root of H. Now unit power. So define as a power developed by turbine working under a unit head, under a 1 meter head denoted by PU. So Q discharge passing through the turbine when the head H is on the turbine. H is a head, P is a power developed by turbine. So P directly proportional to Q and Q into H, but Q is directly proportional to under root of H. So P directly proportional to under root of H into H. So P equal to K3 H raised to 3 by 2. K3 is a proportionality constant. So put unit quantities H equal to 1 and P equal to unit power. After putting, we are getting Pu equal to P upon under root of, H raised to 3 by 2. Hence, for similar design turbines, we can write Pu equal to P upon H raised to 3 by 2, P1 upon H1 3 by 2, like that continuously. Nu equal to P by under root of H, N1 upon under root of H1. Qu equal to Q upon under root of H, and Q1 equal to under root of H1, like that. So today we have covered here total second unit, total theoretical part. In any doubt, any queries, please ask me. In next lecture, we have discussed problem on Pelton wheel, impulse water turbine. Any doubt, any queries, please ask me, all of you. Any doubt?